slides that I hope you'll bear with me, and I haven't given a talk before in this format, of course. So, you know, if I hope, because I can't see any of you guys and you can't see me, I hope that I will be interrupted, as much as necessary to so that I know that I'm connecting to people and that you guys are understanding what I'm saying. So whatever feedback I get, we much appreciated. All right. So I'm going to be giving kind of a survey of the theory of quadratic forms, and in particular some of the more recent developments in that theory. So let me just begin by just setting the tone and going over what are the objects that we're going to be looking at. So, so as you see, we're going to be assuming that we have some given field. This is some field, and we don't really need to make any assumptions in particular about it. It might be the rational numbers, or it could be the real numbers, or whatever. It could be complex numbers and join some collection of indeterminates. The only assumption that we're really going to make, which will become a little more clear soon, is that the characteristic of this field is not 2. And then we're going to suppose we have a finite dimensional vector space over that field. Then what is a quadratic form? So this is a form on this vector space. Q is a quadratic form of V if it is a degree 2 homogeneous polynomial function on the vector space. So for example, if you have a 2-dimensional vector space and the coordinates are given by the 2 functions x and y, so these are just the coordinate functions, then an example of a quadratic form would just be this: x squared plus 3xy minus 1y squared. So these are, the interesting thing about quadratic forms is that they're, it's very easy to define. And at the same time, there's surprisingly questions that come up about these kind of very kind of somewhat naive kind of structures that might seem to be, simple structures at first. So just to just illustrate this point a little bit, some kind of more classical examples of interesting statements about quadratic forms is, well, for example, if you look at just the form x1 squared, why don't I just make this, forget about that one, x squared plus y squared plus z squared plus w squared, then a well-known thing about this form, so this is not really so much about fields as rings, or in particular the integers, is that every integer can be written in the form q of v for some v for a tuple of integers. So in other words, every, not every integer, every positive integer can be written in that way, of course. So this is a kind of a fact that is not super simple, not super obvious at first, but it's kind of an interesting statement about quadratic forms. So this particular form, any integer can be represented in the form q of v. A somewhat more deep result, a much deeper result, is this is what's called the 290 theorem. So this is a result that I think was proved back in 2005 due to John Hankey and Manjul Bhargava. which says that if Q is a quadratic form in some number of variables, and it's integer valued. So, for example, maybe if all the coefficients are integers, then this form would be integer valued for every input that you put in. In other words, for every integer value of these variables, you get an integer out. That's what I mean by integer valued. If you have an integer valued form, then all positive integers are of the form Q of V for some V, if and only if it's true for integers less than or equal to 290. So in other words, if you can write every positive integer which is less than 290 in the form Q of V, then every positive integer can be written in that form. So this is just another example of a kind of a very not obvious statement about quadratic forms. So easy to define, to start thinking about quadratic forms, but quickly one finds questions that are very difficult to tackle. This was, I think, a conjecture of John Conway. I think he must have started thinking about it in the 80s, and it was, took a good 20 years and a fair amount of technology before people understood how to prove it. Okay. Let's see, okay, was that? Scroll back up. There we go. Okay. Was there a question? Oh.
I don't think so.
Okay, so when you first start looking at quadratic forms, it turns out that some are kind of easier to understand than others, and the easiest quadratic form to understand turns out to be the hyperbolic plane. This is a very particular form. It's just a form in two variables. So in other words, this is just a two-variable form. So it's defined on some two-dimensional vector space with coordinates x and y, and it's just the form x times y. If you coordinates this thing, you can also write, maybe I can write this as u squared minus v squared. So changing coordinates where maybe x is u plus v and y is u minus v, this is the same forms. You can think of this in both of these different ways. Why is this form kind of easier to understand? Well, it turns out that the basic, the first thing that you end up looking at with quadratic forms, the first basic thing that you end up looking at is whether or not you have a solution to the equation Q of V equals 0. I should say a non-zero solution to that. So that is to say, I don't, so for example, if this is the form, if this is Q, then plugging in U equals 1 and V equals 1, we see that you get a solution to, Q of that vector with coordinates 1, 1 is equal to 0. So Q of 1, 1 equals 0. So in general, forms for which you can understand, for which you can write 0 as the value of the form are easier to understand. These forms are called isotropic. And forms that do not have that property are called anisotropic. So the hyperbolic plane you can think of as kind of the simplest example of an isotropic form. So written in this way, you can see that you have two obvious solutions to this being 0, 1 times 0, or 0 times 1. In fact, one can show that if you have a two-dimensional form, which is isotropic, it's actually equal to this form after a change of coordinates. So the basic notion of how you compare forms is just by changing coordinates. This idea is encapsulated in this definition. So you say that two forms, V, Q, and W, Q prime, are isometric if there is basically a way of identifying the coordinates on one vector space with the coordinates on the other, if there's a linear isomorphism between these vector spaces, such that the quadratic form on V lines up with the quadratic form on W once you use this linear transformation. Okay. Does everything make sense so far?
Yeah, it does. Just a quick question. So yeah, you're talking about the fact that a form is isotropic if the kernel is non-zero. Is there any connection to group actions where you have the isotropic subgroup? If you take the field of the field of the vector space and you look at you think of a group action of the field on the vector space, is that related somehow to isotropic subgroups, or there's no relation or connection there?
So I'm not sure. Well, one thing to keep in mind is that the quadratic form, so you're kind of thinking of the form as a map, right, that takes a vector and gives you back some field element, if you kind of plug in a vector, right? But this is not any kind of homomorphism.
Yeah.
Right, so there's no real kernel going on.
Mm-hmm.
But in terms, so I don't know what isotropic subgroup would mean. I don't know what that means, really.
Okay. But since the quadratic field, the quadratic form can come from a bilinear map, right? So, if you bilinear maps, so I guess those are trivially, homomorphisms. So, is that just a connection? Just an idea that came out? I just was wondering.
Right. No. And that's interesting. So in fact, well, let's see. So you should, let's see. Something to keep in mind, I suppose, is that I don't know if this will clear things up or not. We're about to talk about the bilinear form, but if you have, for example, if you have your vector space defined over the complex numbers, and Q is a quadratic form, then they will always be isotropic.
Yeah.
But the bilinear forms, there are kind of interesting, kind of non-degenerate bilinear forms. The standard bilinear form will give some non-degenerate form on your vector space, kind of the standard dot product. If you identify this with, Cn, and you just define the standard dot product, you'll get a bilinear form, which is kind of not, it doesn't have any kernel, so to speak. The right term, I guess, is it doesn't have a radical. But it's, being isotropic, you should think of as it's an arithmetic thing.
Okay.
I guess.
Okay.
It's arithmetic. It's not a kind of a geometric or linear kind of idea. It's an arithmetic idea. The point is it's really about, can you come up with a solution to some equation? Like, for example, you could imagine, let me just think of it interesting, you could imagine the equation x squared minus 3y squared is equal to 0.
Yeah.
So what does it take to solve this equation? For example, if your field is the rational numbers, then if you could solve this equation, you would be saying that you would have a solution to x over y squared is equal to 3. If you move this over and divide, then a solution to this equation is a solution to this equation.
Okay.
And then you're really asking, does 3 have a square root?
Yeah.
And that's really kind of an arithmetic question. It depends on what the original field was. If you join a square root of 3, then suddenly, you have a solution, but before you didn't, that kind of thing. So the question of isotropy, this is very much kind of an arithmetic question about the field.
Okay.
And maybe this is kind of an important point, which is kind of a little bit illustrated by the previous examples. I mean, if you
You are now muted.
if you think about these things like the 4 square theorem and the 290 theorem, the 4 square theorem, I mean, one really doesn't think about that as kind of a statement that's interesting because it's something about quadratic forms. I mean, you don't usually think about quadratic forms when you're thinking about these kinds of topics. More, you think about this as an interesting property of the integers, or maybe of rational numbers or whatever. These are interesting properties of arithmetic. And the idea is that quadratic forms are kind of best thought of as like a goal for exploring the arithmetic of a field.
Okay.
And this question of isotropy and anisotropy is kind of an arithmetic question about the field.
Okay.
Which things have solutions, which things don't. Okay, well, maybe
You are now.
is that all right for now?
Yeah,
Or-
that's fine. Yeah.
Okay. So, as we were just discussing, bilinear forms. So, if you have some quadratic form Q on some vector space V, then you can define a bilinear form, usually called B sub Q, such that so this is, so I mean, a quadratic form, you should think of it's kind of like a norm, or like a norm squared, right? It's like the squared length of a vector. Usually that's defined by sums of squares. So that's like a quadratic form. And bilinear forms correspond to dot products, kind of in terms of our intuition. And so, given a bilinear form, you can express the norm of a vector just as taking the vector and dotting with itself. And this is one way of a bilinear form, you can get a quadratic form. But it actually goes both ways. So if you start with a quadratic form, you can also define this thing B sub Q. And the formula for it is, maybe I should, let's see. So the formula for it is that if I wanted to say what's the dot product of V and W, then there's this kind of well-known identity that lets you write that down. It's the quadratic form on V plus W minus Q of V minus Q of W, and then divided by 2. So this gives a nice kind of back and forth relationship between quadratic forms and bilinear forms. If you have a quadratic form, you can define this bilinear form. If you have a bilinear form, this gives you a quadratic form. And this gives you a nice kind of bijective correspondence between bilinear forms and quadratic forms. The only trick is you needed to divide by 2 to do that. So this is why we generally assume the characteristic is not equal to 2. There is a very nice, well-developed theory of quadratic forms when the characteristic is equal to 2. It's just somewhat different because we allow ourselves, when the characteristic is not 2, to go back and forth between quadratic and bilinear forms depending on whatever is convenient. But this is not a trick that's available in your toolbox in characteristic 2. You have to modify it. But anyways, we'll just assume that the characteristic is not 2, so that we can freely go back and forth between quadratic and bilinear forms. So a quadratic form is called regular if the associated bilinear form is non-degenerate. So this is, so what does this mean? It just means that if you have a vector V, So I should just say from now on, we'll go back and forth between the quadratic form, between the Q and the bilinear form. These two objects contain the same information, so we should think of a quadratic form as really the same as a bilinear form and vice versa. So given our quadratic form and its associated bilinear form, we call it regular if it's, what did I say? If it's non-degenerate, that's the word, right? And so what does that mean? It means that you can tell if a vector is zero by saying, is there something that by seeing whether or not it pairs with everything else zero. So in other words, one way of saying this is that a vector is zero exactly if it pairs zero with all other vectors. Or as I've said it here, if you have a non-zero vector, then there must be something that you can put in this blank to get something non-zero. Okay, or another way of saying it is that you get an isomorphism between the vector space and its dual by mapping any vector to the function which dot products with that vector. So this is the notion of regular forms. So we're going to generally work only with regular forms. So I'll just say we'll be working with just regular forms. The forms that are not regular, maybe if I have time, I'll say a little bit about it. I mean, basically, you can always take an arbitrary form and break it up into two pieces, one of which is kind of maximally regular, and the other part is really just zero. And so it's kind of like the non-zero, non-trivial part of any quadratic form is kind of a regular part, and you can kind of reduce the general study of forms just to regular forms. So I might say a little more about that, but for now we'll just assume that we're working with a regular form. Now, one thing that makes life very nice when you're working with quadratic forms is there's this process of diagonalizing the form. So if you have some arbitrary form, x squared plus, I probably won't try to do this too concretely or else I'll probably just get confused, but if I have some quadratic form, then the theorem is that you can change coordinates to maybe some, to change to some new coordinates, say u and v, such that if you rewrite your form in terms of u and v, it's diagonal, so that means it looks like a u squared plus b v squared for some a and b. The procedure for doing this is kind of the classical Graham-Schmidt diagonalization process that you learn about in linear algebra for finding an orthogonal or an orthonormal basis for a vector space with respect to a bilinear form. The basic idea is you start with v non-zero, and then you pick some w which is perpendicular to v. In other words, that, oh, whoops, what did I do? I clicked something by accident. Pick some w which is perpendicular to v, in other words, such that the bilinear form evaluated on w and v is zero, so that's just what I mean by perpendicular. And And why can you do that? Well, it's because if I look at form B of blank comma blank comma V, this is a homomorphism from V to F. So this is from a fairly large vector space, or some n-dimensional vector space, to a one-dimensional space. If there is anything left in big V besides little v, then this thing has a non-trivial kernel, and I just picked some W in the kernel. This V basically corresponds to my first coordinate over here. I should have called it V, but I didn't. And then the W will be my next coordinate, and you just keep kind of picking things that are mutually perpendicular to everything that you picked before over and over, and you will eventually express your form in this kind of a way. With nice compact notation for these forms, because they tend to come up over and over. So the notation is that a brace, let's say, I don't know, A, B, C, D, for example, would mean the form ax squared plus by, y squared plus dz squared plus dw squared. So, a list of four numbers corresponds to this form. And the great thing is that you can always write an arbitrary quadratic form in this way. And so really the only information is just kind of contained in these four numbers about what the form looks like. Okay. So, so I said before, kind of the main question that one typically asks is, if you have a quadratic form, which again we'll assume is regular. In other words, the bilinear form is non-degenerate. Then you can ask, well, is it isotropic? In other words, can I write can I find some v non-zero with q of v equals 0? It turns out that if you can write that, the reason is the only reason that forms are isotropic is because of the hyperbolic plane. So remember, the hyperbolic plane was this form which either looks like xy, or in other coordinates u squared minus v squared. So this generally has the name h, and the theorem is that if this happens, if q of v is equal to 0 for some v non-zero, then there exists some, let's call it some subspace H V with if you take a quadratic form and you restrict it to H, you just get something isometric to that form right there, to this, to the hyperbolic plane. So in other words, there's some two-dimensional subspace of your vector space such that it looks like a hyperbolic plane there. So the only reason the point is that the only reason that a quadratic form might be isotropic turns out to be that it contains a hyperbolic plane. Moreover, there's a natural way that you can kind of take different quadratic forms and kind of combine them to make a new one. It's this thing called the orthogonal product. So if you have VQ is one quadratic form in a vector space, and if I have some WQ prime, you can form this orthogonal sum in the following way. So as vector spaces, what you do is you just take a product of the two vector spaces, and then for the forms, well, maybe I'll just write it as Q perp Q prime, but how is it defined? So if I have Q perp Q prime, so this is going to be a function, we can think of it, which takes a pair V comma W. And it's just defined by evaluating the first on the first and adding the result to evaluating the second on the second. So just as a silly example of the form 2x squared plus 3y squared, and I perp that with a form, 5z squared minus 2zw, then what is that? It's just the form in 4 variables, 2x squared plus 3y squared plus 5z squared minus 2zw. You just stick them together, making sure that all the variables in here are distinct with the variables in here, and the form is just what happens when you add them up together like we did over there. So underlining minus. Okay, well, why did I mention this now? It turns out that that given any form QV, there's this thing called the Bilinear condition, which says that I can write Q as isometric to, let's say for something which I'll call Q ani perp Q hyperbolic. So in other words, I can break up the underlying vector space V into two parts. So if this is V, then I'm saying that V is actually the same as some V prime cross some V double prime corresponding to this and corresponding to that, such that the quadratic form on the on this V prime part, this Q ni, is an anisotropic form. And the hyperbolic is of the form, H perp, etc. So the idea is that if you have an isotropic form, one where there is a vector where you can get 0 in a non-trivial way, then you can find a hyperbolic plane sitting inside of this V, and you can pull it out. And then you can keep doing that and keep pulling out these planes until the thing that you are left with, this Q anisotropic, doesn't have any more hyperbolic planes in it, and therefore is no longer isotropic. So there's no way of solving this equation in this with this form on this vector space. Okay. So now it feels to me like I've just been talking and talking and talking.
I think it's yeah.
How's it going over there?
Yeah, I think it's quite clear. I mean, so far, I think it's quite clear. But let me ask the University of Ghana. University of Ghana is. Do you have any questions or comments to ask? Or hello?
Yeah, we're here.
Okay. So, do you have any questions? He's asking whether you have any questions to ask. Or? Yeah. Mm-hmm.
No questions.
Okay.
Have any of you guys seen the bit group before and hyperbolic planes and isotropy and these things before?
Some people have. We have a mixed audience in the room.
Okay. Mm-hmm. Okay. Well, Well, just please stop if you can, if you'd like to. Okay. We'll just move along.
Yeah.
Let's see, where were we? Right, that's right.
Yeah, so we're happy to continue.
Okay, great. So, so I'm just trying to, oh, by the way, when I move my pencil across the screen, I'm not writing right now, but I can see a little red dot. Do you guys see the red dot as well?
Yeah, we do.
Okay.
Yeah.
Okay, good. So, let me just say a few more things about kind of setting up the basic language of talking about quadratic forms. The really interesting, one interesting thing about them is you can kind of stick them together to form a group and even a ring. So so again, we're fixing some field F, it's just some fixed field with characteristic not equal to 2. And if I think about these quadratic forms, well, we have some basic operations that we can do. If you have two forms, you can group them together, as we did on the previous slide. So this just means take the product of the vector spaces and take the sum of the two forms. This corresponds to kind of an addition type operation. And there's also an operation corresponding to times called the tensor product. So how is this defined? Well, if Q is a form on some vector space V, and Q prime is a form on some vector space W, then this is a form on V tensor W. And well, let's see. So maybe the easiest way to define it is by defining the associated bilinear form. That's probably the least confusing for me. And then you can get from that the quadratic form. So the bilinear form on a pair of vectors, well, because this is linear in both coordinates, I can reduce to the case of considering vectors of the form V tensor, how about V tensor V prime, comma, W tensor W prime. So in general, everything in this tensor product is a sum of vectors of this form. But again, because this is a linear function in both variables, I can just reduce to considering what it does on these elements which span. And the definition is that this is, well, you take the value of BQ on the first vector, on the first part of these, and you multiply it by BQ prime on the second part. Oops, V prime, W prime. This is also kind of relatively easy to make sense of if you think about it in terms of a diagonal form. So you find, for example, so I won't kind of go through the whole translation, but the answer turns out to be kind of straightforward. So just by way of example, what happens if you, tensor these two forms together? This is going to be a form, I wrote a lot of variables out. This is going to get kind of big. Maybe I'll start writing and you'll see the pattern. What the tensor looks like, so this is let's see. So the new form is going to look like AD times, maybe I'll just make capital letters for my new variables, x squared, plus AE y squared, plus BD z squared plus just all combinations of pairs of vectors, where this capital X would correspond to the kind of X tensor U in this case. That's where that term is coming from. This Y corresponds to X tensor V, etc. Well, except for maybe in the other notation, it's even simpler to think of. If I have A, B, C, that's this form, and I tensor it with D, E, then I get the form A, B, A, E, B, D, B, E, C, D, C, E. It's easier to write if I don't have to think about what the names of my coordinates are. Okay, so these two operations give you ways of taking a quadratic form and getting a new quadratic form. You don't quite get a group or a ring yet. I mean, you almost do. The only problem really is you don't have negatives. So what you can kind of fix this problem by just declaring an equivalence relation that Q is equivalent to Q prime if they have the same anisotropic parts. So recall from the last slide that given any form, there's a unique way of breaking it up into a part that's just a bunch of H's, a bunch of hyperbolic planes, these kind of easiest to understand two-dimensional form, and an anisotropic part. And so all we're saying is that we call two forms equivalent if they only differ by maybe having different numbers of hyperbolic planes, but outside of that, their anisotropic parts are actually isometric. If you do this, then it turns out that this makes the equivalence classes into a ring if you use these two operations. So these two operations extend to operations on these equivalence classes, and they give you the structure of a ring. This ring is called the Witt ring. So the punchline is that elements of this ring correspond to isometry classes of anisotropic forms. So, and these are really the most interesting forms anyways. I mean, everything is anisotropic plus some number of hyperbolic planes. Hyperbolic planes are kind of not the interesting structural part of the form. It's really the anisotropic part that's interesting.
So for the Witt ring, is the multiplicative structure comes from the tensor product, right? If I understood you rightly.
Yes.
Okay.
That's right. So this is the multiplication, and this induces the addition.
The structure. Okay.
Yeah. So there are some things to check. I mean, why do forms have negatives really, and why are these operations well defined on equivalence classes, and that kind of thing. It turns out that the easiest way to understand the negatives is if you think in terms of that notation with these diagonal forms. When you add things, that's just the same as concatenating. And what gives you negatives is the observation that if you have a form and you stick a minus in front of that same element, in other words, if you look at the form A minus A, it turns out that you can always show that that's the hyperbolic plane.
Okay.
And so, if somebody gives you an arbitrary form, A, B, C, D, whatever, then if you perp that with minus A, minus B, minus C, minus D, then combining these kind of pairwise, you just find that you have 4 hyperbolic planes,
Okay.
which are now called 0 in this new equivalence relation.
Okay. Thank you.
Sure. So let's
now
see.
muted.
Okay. So, let's see. I guess I should think about my timing too, because I see that I'm halfway through my slides and
You are now
3/4 of the way through the time.
Yeah.
So let me think about that. Okay, not a problem, I guess. George, I should 12:30 or what?
You can go beyond a bit beyond that. That's fine.
Okay, well, I'll try not to be here all day, but maybe I'll go a few minutes over.
Okay, that's fine.
Okay. So, right. So that's the question now becomes trying to understand the structure of this bit ring, and in particular trying to determine whether elements are trivial or are not trivial in the bit ring. So this is kind of the main question. So the question is given. Here's one way of saying it. So given a quadratic form, how can we determine if Q is similar to 0 in the bit ring? Why is that an interesting question? Well, it's really the isometry question. Because really what it's saying is, because now we have a ring here, if I have 2 different forms, Q and Q prime, and I want to know if they're isometric, are these isometric? Well, first off, they had better have the same dimension. Or else there's no hope. But once they have the same dimension, you can consider their difference in the bit ring, and you can ask, is this difference 0? So if this difference was equal to 0 in the bit ring, so if you knew that, and then that would tell you that Q is similar to Q prime, which would tell you by the definition of similarity that they differ by some number of hyperbolic planes. Bunch of hyperbolic planes. But it turns out that this anisotropic part, well, I guess I should say that then Q also is Q anisotropic for, again, a bunch of hyperbolic planes, and this right-hand side is Q prime aniso for some hyperbolic planes. If this thing over here is isometric to this thing over here, with all these H's, and it turns out that this anisotropic part is actually uniquely defined, determined. These will actually be forced to be isometric themselves. Q ani will be isometric to Q prime ani, which then if you add those hyperbolic planes back in, you'll get that this is actually an isomorphism. And that answers the question. So the point is that if you understand which things are 0 in the bit ring, you can answer the question of which forms are isometric. So the real question is, what tools do we have for understanding when things are trivial in the bit ring? So this question boils down to what are called invariants. So in other words, we're looking for ways of taking elements here, and we're looking for interesting homomorphisms. So that if somebody gives us a form, I'll call this E, this homomorphism, if somebody gives us a form, we can measure we can look at its image in this other abelian group and decide whether or not this is equal to 0. The idea being that these other things hopefully will be easier to understand than the original bit group. So, so what are some examples of these invariants? The first invariant is, well, the dimension. You know, as you might, you know, have guessed from this particular example before. In fact, you know, if you want to speak strictly, the dimension of a form, so this would be, what is the dimension? It's an integer. So we would want to map to the integers, but it's not really well defined because these things are equivalence classes where you can add arbitrary amounts of the hyperbolic plane. So since the hyperbolic plane is two-dimensional, you're allowed to add as much even integer or subtract as much even integer as you want to keep the same element here. So to make it well defined, you actually have this dimension mod 2 map. The kernel of this is called I of f, and it's called the fundamental ideal. There's nothing deep happening here. This is just the even dimensional forms. One of the most mysterious things about quadratic form theory is that this very innocent object, I of f, with this very naive and simple definition, the even dimensional forms, turns out to kind of be the key to understanding the structure of the bit ring in many ways. So, okay, well, let's move on to the next example. So this was a very kind of trivial invariant, the dimension mod 2. Another one is called the discriminant. So so how is this defined? Well, so one way, let's see, what's a good way to define this? Well, one way to do this that is typically discussed is if you have a bilinear form on your vector space, then classical linear algebra tells you that to evaluate the bilinear form on a pair of vectors, you can find some matrix, we're going to call it capital B, such that the form looks like V transpose matrix multiplied by B multiplied by W. And the determinant of the form Q is defined to be the determinant of this matrix B. Well, this is almost well defined. Again, there's an issue, which is, you know, does this depend on your representative? Does it depend on adding hyperbolic planes and things like that? It turns out that you can kind of change coordinates on your vector space and see that this function is not really well defined on VIT equivalence classes. So, I mean, a priori, this is going to be an element of f, and it turns out that it's always non-zero if your form is regular. But it's not really a well-defined function on equivalence classes, but it is well-defined if you look modulo squares. So if you change coordinates, this determinant might change, but it will always change by square. Okay, so this is, and now so now this is some extra information. It's not quite, unfortunately, a homomorphism, but it turns out that if you, so I just said it's well defined, it's just not a homomorphism. So we want to construct this map W of F to F star mod F star squared. Of course, we have a map, but we'd like it to be a homomorphism. And it's not quite, but if you restrict it to I, and you modify the sign of it, then it does become a homomorphism. So the map is Q goes to what's called the discriminant of Q, which is the determinant with an extra sign, minus 1 to the, and actually, you know what, I can't remember what it is. It's something depending on the dimension, but I can't remember what goes up there. I can't remember. It might be, I think it might be the dimension of Q minus dimension Q minus 1 over 2 or so. I wish I'd looked that up, but I don't remember what it is. I can never keep that straight. You have to adjust it by a sign just to make it into a homomorphism. If you don't put the sign there, you get a well-defined map, but it's not a homomorphism. Okay. So, taken together, what you find is that, so what's the structure of what we have so far? You have this map, W of F goes to Z mod 2Z. This is the dimension, mod 2. Its kernel is called the fundamental ideal, I of F. Then you have the fundamental ideal. It maps by the discriminant to F star mod F star squared. And its kernel turns out to be, strangely, the square of the fundamental ideal. So in other words, all things that are of, it's the ideal generated by everything of the form Q tensor Q prime, where Q and Q prime are even dimensional.
So is there any particular choice of the finite field Z2 or any field of any field could work? If you have like this is ZP, would that work or?
You're wondering why the 2 here?
Or why the finite field Z2?
The question was this, right?
Yeah.
Well, the reason for the 2 is that 2 is the dimension of the hyperbolic plane.
Oh, okay. So this will not work for any other finite field.
No. This is just something very special about 2
Okay.
in this case, because the point is that Q has to go to the same place as Q if I perp it with the hyperbolic plane.
Yeah.
Because these are equivalent, and if this is well defined on equivalence classes, then these two things have to map to the same place.
Okay.
So it's just a fact that we're always allowed to add 2's to the dimension, and we're supposed to get the same answer.
Yeah. Okay.
Right. Okay, so it turns out that sometimes this is enough to tell you everything you'd like to know. I'm sorry. There's some. Could you? I'm sorry. There's some knocking at my door. I'll just tell them to go away. I'll be right back.
Yeah.
I'm sorry.
Okay. That's fine. Yeah.
Sorry.
Okay.
You are now muted.
Hey, I'm just giving a lecture right now. Okay. Thanks. Okay, back. Sorry. I was hoping they would just go away, but they were persistently knocking.
Yeah,
So.
that's
You are
fine.
now unmuted.
That's fine.
Okay.
That's all right.
Okay, so it turns out that sometimes this is enough information to really tell you everything you'd like to know. So one example when this is enough is, let's say, for a finite field. So f is a finite field, of course, characteristic not 2, but any other characteristic is just fine. Then it turns out in this case that well, two things turn out to be true. That if Q is anisotropic, then its dimension is less than or equal to 2. So it turns out, this is just a fact about finite fields, that if you have a quadratic form in 3 or more variables, it can never be anisotropic. Another thing that's true is that if the dimension of Q is equal to 2, then the class of Q being in the square of the fundamental ideal implies that Q is trivial. So in other words, it turns out that you can show that everything in the square of the fundamental ideal must necessarily have dimension at least 4. It turns out. Not every non-trivial thing has to have dimension at least 4. And so if you have dimension 2, you have to be trivial. So what this says, if you put this together, is that we have a complete criteria for understanding with a form over a finite field is trivial in the Bitcoin. Answer is you first check its dimension. If the dimension is even, then you're in I of f. And if you're in I of f, then you apply the discriminant. If your discriminant is a square, then you're in I squared of f, but that means that you're 0. And you're done. So the interesting thing that we use here to understand this is, one of the most important facts here is this first one, which turns out to be a very nice kind of property that we try to generalize. It's called the U invariant. So definition, U of f equal, U of f is the maximal dimension of an anisotropic form. The interesting thing about this invariant is that sometimes it exists, and sometimes you can calculate it. So for a finite field, the U invariant is 2. For the rational numbers, well, it's actually infinity because you can have a sum of as many squares as you'd like. And you can never solve, this will never be isotropic. You can never solve a sum of positive numbers equaling 0 unless all of these things are 0. On the other hand, if you're interested in arithmetic things, all hope is not lost, because it turns out that the U invariant of, let's say, K, where K is an imaginary number field, or a p-adic field, or a global field, there's still a very constrained structure on the size of quadratic forms, so long as you stay away from kind of the real places, the fact that you can have that you have orderings on your field, and you can have things that are positive. Okay, So, well, now for number fields, for example, and for these other fields with U invariant 4, these two invariants that we defined turn out not to be yet enough to understand whether or not things are isometric or not. Or that is to say, whether or not things are 0 in the bit group. So if you have a form of a number field, you can do this procedure, check if its dimension mod 2 is 0, then you're in here, and if you're in there, you can take its discriminant, and then you're in there. But now, there's the question, well, what if you have something in I of f squared? How can you tell if that's 0? So maybe you can probably see the pattern now. The pattern is, you'd like to understand something like this. Like if I have I squared, I want some other invariant that maps this to some other place. And well, in the last example, it was I got mapped to f star mod f star squared. Oops. And the kernel was I squared. And now we have I squared mapping to somewhere, and it turns out that we're going to look for a kernel of I cubed. And you might just try to continue this game and see where you can go.
You are now on.
It's a big kind of question mark. Can you actually do this?
So are you forming a sort of an exact sequence, or?
Yeah, well, a priori, yeah, these are exact. That's right. These are all exact sequences.
Yeah.
A priori, I'm not saying anything about the exactness on the right.
Yeah.
Although they will be all exact on the right, it will turn out.
Yeah.
But yeah, that's right. That's right. Okay. So you can kind of think of this as like kind of peeling this group like kind of an onion. You know, you're looking at kind of smaller and smaller layers. And seeing how deep down a quadratic form is, you know. Somewhere at the bottom of all this is 0 that you're trying to figure out. You want to say, is your form 0? Is it in there? Is it in there? Is it in there? Hopefully, if it's in all of them, you can show that it's 0. That's the strategy.
Okay.
Now, so there is a nice invariant that goes here. The group turns out to be what's called the two torsion part of the Brouwer group of the field. Roughly speaking, how is this thing defined? So this here is called the Clifford invariant. It's a bit of a long story, so I won't give the full details. But what you find is that given a quadratic form, you can define this thing called its Clifford algebra, which has nice uses in a lot of other areas like physics. The Clifford algebra, it's this fairly large non-commutative algebra where the elements look like products, kind of formal products of vectors in your original vector space. And sums of products of, some products of vectors in your original vector space with the new, which don't necessarily commute. So there's no assumption that VW is WV. But the identity that if you square a vector, that's the same as evaluating the quadratic form. So this just gives you a way of writing down generators and relations for some just big algebra called the Clifford algebra. And this algebra itself you can think of as an invariant of the quadratic form. So the elements of this are equivalence classes of associative algebras. Together with some kind of multiplication structure, it's an abelian group, so you might call it addition, I suppose. But some kind of option on these algebras, taking two algebras and constructing a new one. It's actually the tensor product construction. If you've seen the tensor product of two algebras, that's the operation. And I won't say what the equivalence relation is, but it kind of is reminiscent of how the original Vit group was constructed, you know, having kind of a tensor-like operation. Well, this actually was the plus, I suppose, but having an operation and sort of equivalence relation when two forms are equivalent, so there's some kind of an equivalence relation of these algebras. And you get a nice group there. This is still relatively classical. I'm not exactly sure when this map was defined, but it was a fair while in, I think. At least Minkowski must have known of it, I think. So let's see. So okay. So it turns out that if you're interested, for example, in number fields, then at this stage, you're done. At least, you know, imaginary number fields. That is to say, if you have quadratic forms which have the same dimension mod 2, and they have the same discriminant, and then they have the same Clifford invariant, these algebras are equivalent, then you land in I cubed, and it turns out in this case I cubed is 0 for these imaginary number fields. Of course, so for number fields that ends the story, but there are many other interesting fields for which things are still very much wide open. The simplest example of a field which we know very little about, oh, I see. I meant to write all that on this slide, I guess. Right. The next, a very natural kind of field which we know very little about are fields such as, well, let's see, pick your favorite imaginary number field and adjoin a single indeterminate. We really don't have a similar kind of structural statement that says that we know the maximum dimension of a form over this field. We believe that the number is 8, but we don't know if it's bounded at all. So for all we know, it's possible over this field to write down a 500-dimensional form, which is anisotropic. We don't think that's true. We think that the largest forms which are anisotropic have dimension 8 over this field, but we don't know how to prove it. So like almost nothing is known. On the other hand, we do know a bit more about these invariants, and that's maybe the last thing that I wanted to really say, which is these, in this picture back here, that I was starting to sketch here, how far down can we push this diagram? So as I said, this stuff above the line is relatively classical, but to define the next invariant, and even to understand where it should go, this is relatively recent. So I think the next step was constructed in the early 80s, I believe, by Arison. So this next thing is called the Arison invariant. And it lives in what's called the cohomology group H3F with Z mod 2 coefficients. It turns out that all these groups that arise on the right, this F star mod F star squared, this Brouwer group it's called, Torsion-Brouwer group, and this H3, these are all examples of what are called Galois cohomology groups. The general picture is that we expect that if you have something in the nth power of the fundamental ideal, then there should be a well-defined map taking you to the nth Galois cohomology group, that it's surjective, and that the kernel should be in plus 1. I think by some point in the mid-early 90s, we knew up to n equals, we had 3 definitely, we had most of 4, and some parts of 5, I believe. You know, we didn't have we didn't know this was exact, but maybe we knew that, I think we knew some of the search activities, and we knew some cases where, I can't exactly remember what we knew, but we just had a little bit more than 3, basically. In the late 90s, this was completely solved by Blavatsky. And later was fully kind of put together by, in this paper of Orlov, Vishik, and Blavatsky. It might be interesting to just comment, like, what are these groups? Because they're, I mean, as we've written it, there's kind of, they're perhaps a little bit mysterious. You can define them in a kind of an elementary way using generators and relations, but it's maybe not kind of obvious what motivation is if you just write it that way. I don't know if it's obvious this way either, but one way of doing this, one way of explaining what this group is using topology. If you let G be the Galois group of this field, then you can construct a space, a topological space that's usually called KG1, and it has the property that it is it's connected. Its fundamental group is exactly G, and its universal cover is contractible. This is a kind of a topological model of the arithmetic of F you can think of. And then these cohomology groups, Hn, F, Z mod 2Z, are just the Z mod 2 singular cohomology of this space. So this is perhaps not kind of illuminating in terms of computing these very easily, but you know, this is at least some definition of these groups. You can write these down, you know, to some extent and work with them just kind of concretely with generators and relations. And they tend to come up a lot in various arithmetic contexts. These things are, you know, just a series of groups associated with the field that just tend to come up in a lot of applications and carry information. this connection to quadratic forms, it goes both ways, both by telling you how to determine if a quadratic form is trivial, and by helping you study these structures that come up in other ways in this group. So kind of like a back and forth play in terms of how this has been applied. So okay, so let's see. Right. So this remarkable work of Orlov, Vishik, and Blavatsky to prove this actually ended up giving a nice kind of three-way relationship between the Vit group and its various fundamental ideals, powers of the fundamental ideal, the cohomology groups, there's no containment there really, these are just a sequence of groups. And it turns out it also gave this interesting relationship between what's called Milnor K-theory. Yeah, I'll just show that. Well, okay, so Milnor K-theory on the left, actually, sorry, K0, K1. At the end of the day, what this theorem gave us is a three-way relationship between these three groups. And the nice thing about it at the end is that so these groups are very easy to write in terms of generators and relations. These things have very concrete interpretations because they're quadratic forms, and we know kind of what that means. We can kind of write down what a quadratic form is easily. And these things on the right are somewhat more mysterious arithmetic objects. Which, you know, come up in various places. So the punchline of Orlov, Vishik, and Blavatsky of why it's interesting is that it gives this interplay between these three things. I mean, you know, my advisor told me, you know, that the usefulness of math is the ability to take an object and have multiple interpretations, so that you can put those interpretations off each other. You know, some questions are easy to answer over here, are hard to answer over here, so you can translate them from here to there, and other things you can answer easily here, etc. Okay. So, okay. So let's see, where are we? I think I basically would like to just finish this off by saying, you know, so we now understand this nice system of invariance. So we now have a nice system of invariance for determining if Q is equivalent to 0 in the Vit group. Many questions are still open. So the two that I'd like to just advertise as particularly interesting is calculating U invariance of fields. For example, the the case that I gave before, if you have an imaginary number field and some function field over that, you'd like to know, we believe, that if the dimension of Q is bigger than 8, then Q must be isotropic. There's kind of a way of interpreting this back in terms of a question about number fields. One way to say this is like, what is a quadratic form over this field? It's really so you should think of it as all the coefficients of the form are functions of t. So it's like a family of quadratic forms parameterized by t. And this is like saying if you have a family of quadratic forms where each quadratic form has dimension bigger than 8, then you can not just say that each individual form is isotropic, but you can come up with a formula in T for how to find isotropic vectors for each value of T. So, an isotropic vector would be a vector whose coefficients are functions of T, which is isotropic. So it's like finding a family of solutions. So there's this question about the U invariant, and then there's still more questions about invariance of forms. For example, we understand, that there's this sequence of invariants. First, you go from the bit to the dimension mod 2, to z mod 2. Then you go from I to this, and you go from I squared to that, etc. But what about just invariants that start from W and go to places? What if you don't look at these things defined on I and I squared, but you just look at invariants defined on W? Which of these are actually defined on W? You can completely classify these. It turns out that's a classical thing. These are called the Stiefel-Whitney classes. But you can similarly say, well, what are the ones that go from I? What are, I know one of them is the discriminant, but what are the other ones? I believe those are also classified fairly recently. But that's about all we know. We know W and I. So it would be nice to understand what all the different measurements you can make at each different stage. That would also give you information about invariance turns out, for other kinds of interesting algebraic objects besides quadratic forms. If you had some of these other invariants, you would have some extra information about related objects as well. Okay, that's about all I had to say. So let me end the talk here, and thanks for your extended patience.
Thank you very much, Danny. Let's see whether anyone has any questions. University of Ghana, do you have any questions to ask?
People are just sitting here.
Yeah.
No questions? Questions? They say no.
So no, okay. Well, I guess then that ends the talk for today. Then.
Okay.
Yeah.
Okay.